Hello students and welcome to lesson 7.05 dealing with Le Chatelier's principle. As always, first let us just talk about some standards real quick. There are some common core standards that we will address in this lesson. So again, if you would like to read over these, please pause the video at this moment and look at those. You can also access these by going to course information and clicking on standards. The objectives for this lesson will be able to predict the effect of various factors on an equilibrium system. And we'll get into the different factors that we're going to look at, but by the end of the lesson you'll be able to look at a system in equilibrium, see what is happening to the equilibrium, and predict where it will end up after that stress has been applied to the system. Now, to be able to do Le Chatelier's principle, you have to have an understanding of equilibrium. So make sure that you have done lesson 7.04. If you're still uncomfortable with that, please review that lesson. And also you can attend the open tutoring sessions that we have to get some more help with that. But be sure you're comfortable with 7.04 prior to attempting 7.05. So again, just real quick, equilibrium is a state in which opposing forces are or influences are balanced. So if you look at the skateboarder here, the question at the bottom, what if he puts more weight on his right foot? Okay, so if he pushed down more on this side, of course we all know that's going to tip the skateboard that direction. And that's how they keep themselves balanced when they're going down the rails here, is pushing back and forth on their left foot or right foot to keep things in equilibrium. Well, reactions do the same thing, and we're going to look at some of those different scenarios. So Le Chatelier's principle simply says that when a stress is applied to a system at equilibrium, the reaction is going to shift in a direction that relieves the stress, and then it's going to establish a new equilibrium. The three types of stress that we're going to look at are changing the concentrations, changing the temperature, and changing the pressure. These are the three we're going to look at. So let's just go ahead and look at each of these one at a time here. Alright, now before we look at each of those individually, we do want to mention the possible scenarios. Okay, the first scenario says we could increase the forward reaction. So if you look down here at the bottom, we've got the generic formula, A plus B yielding CD, and then of course it's reversible, so that's why we had the double arrows. And they're saying if we increase the forward reaction, okay, so we increase it going this direction, then we're going to cause the system to shift to the right. Which again, if you just kind of be logical with it, that makes sense, right? If I'm having A and B reacting more and producing C and D, then clearly my equilibrium is going to shift over here to the right. Okay, well the opposite of course would be true. If I increase the reverse reaction, or the rate of that reverse reaction, then it's going to shift the equilibrium to the left. Okay, so just the opposite. Now we could also do a decrease. Alright, so we represent decreasing with a smaller arrow. So if I decreased the forward reaction, alright, so if I decrease this forward reaction, then what's going to happen is the reverse reaction is going to compensate for that. So that's actually going to cause a shift to the left. So a small forward arrow, if you will result in a larger reverse arrow, if you want to think of it that way. And it's going to, again, compensate for that difference and shift the equilibrium to the left. So, of course, the opposite of that would be true. If we had a decrease in the reverse reaction, then it will shift it to the right. Okay? So, basically, if you kind of think of this like a seesaw, and right here in the middle, okay, this is the middle, the tipping point. If I increase the left side, then it's going to shift it towards the right. Okay? Again, just kind of think of it like a teeter-totter. If the left side goes up, the right side goes down, and so on. If I decrease the left side, then it's going to shift it towards that. Okay, so these two go together, and then these two go together. All right, and that's really all it's talking about, those four scenarios. We're either increasing one way or the other, or decreasing one way or the other. And each of those three stresses are doing exactly those things. All right, so let's look at the concentration one first. Let's say we have this reaction. We have nitrogen plus hydrogen giving us ammonia. If a reactant or product is added to the system, then the equilibrium shifts away from where we just added it to the lower concentration. Alright, so in other words, if we add, let's say, nitrogen, then we have more nitrogen that is going to be able to react with the hydrogen. So that is going to cause the equilibrium to shift to the right. So of course, if I added more ammonia, then it would shift the other direction. It would shift to the left. If we remove one of them, then it's actually going to shift towards it. Okay? So if we remove some nitrogen, just using this one as our example, then there's kind of a gap there, if you will, or there's like an empty vessel, however you want to think of it, and we need to fill it back in, so the equilibrium is going to shift towards where we removed it from to replace the nitrogen that was removed, if you want to think of it that way. Okay? So if we add, it shifts away, because that throws the balance off, and it's got to reestablish equilibrium. If we remove, then we have to refill or replace, so it's going to shift towards, and again, that's going to reach a new position of equilibrium. So let's look at a couple examples here for the concentration shifts. Alright, in the first one, I've got hydrogen plus oxygen yielding water. If I increase oxygen, which way would it shift? Okay, so if I am increasing the amount of oxygen, so oxygen goes up, I like to use arrows to kind of put it in a picture form for myself, then that means it's got to shift away. So this is going to shift to the right. Okay, again, if we increase concentration, it shifts away. Simple as that. Alright, for the second one, we have nitrogen monoxide and oxygen producing nitrogen dioxide. So in this case, it's asking, what if you decrease the NO2? Okay, so again, the NO2, if I'm decreasing, if I'm removing NO2, then I have to replace or refill it. So it's also, in this case, going to shift to the right. Okay, so again, if you increase, it shifts away. If you decrease concentration, it shifts towards. Alright? Okay, now let's look at temperature. Before we look at how it shifts, we need to look at where we place energy in balanced equations. Okay? If the forward reaction is endothermic, which we learned back in Module 6, then the reaction, or excuse me, the energy is a reactant, and we write it on the right, or excuse me, the left side of the equation. Okay. Again, remember, endothermic means energy is entering the system, so that means it's being added, so it goes on the left side of the equation. If it's exothermic, then it would be just the opposite, because it's exiting the system. So we're going to write that as a product on the right side. So anytime you see energy on the left side, that's endothermic. On the right side, it's exothermic. Now the principle that applies there is basically the same as what we were just doing in the last one. If I increase temperature, then I am also increasing the amount of energy that the molecules have. Okay? Remember, temperature is a measure of the average kinetic energy. So if I am increasing the temperature of the system, that also means I must be increasing the energy. So if I use this first one as my example, if I am increasing the energy, again, that means it's going to shift away because it has to get rid of some of that energy to get back to a state of equilibrium. So if it's endothermic and I increase energy, it would shift to the right. If it's exothermic and I increase energy, then it's going to shift to the left. Okay, so it's very important to know, am I dealing with an exothermic reaction or endothermic reaction, because that determines which direction it's going to shift. All right, so again, let's look at a couple examples. In the first one here, we have an endothermic reaction where we got dinitrogen tetraoxide changing into nitrogen dioxide. If energy is added to the system, which way will it shift? So again, we're adding energy, so we're increasing the energy. That means it's going to shift away, so it's going to shift to the right. Okay, same principle that we use with concentration. If you increase, it's got to shift away so it can react and remove what we just added, basically, or at least a portion of it to reestablish equilibrium. In the second one, we have carbon reacting with oxygen to produce carbon dioxide and energy, an exothermic reaction. And it says if energy is removed, which way will it shift? Okay, so we're removing energy, so it's going down. So we have to shift towards that to replace or replenish it. So that would shift to the right. Okay, and that's how we do the temperature. All right, now the last one was pressure, and we're actually going to look at pressure and volume together. Going back to Module 5 where we did the gas laws, if you look at the second bullet here, remember that by decreasing volume of the container, we're going to increase pressure. Smaller area, or excuse me, smaller volume for those particles to move around in. They're going to collide more frequently with the wall of the container. That's going to increase the pressure. So a lot of times you may hear those terms used interchangeably. You know, I decrease the volume or I increase the pressure. Realize that they're meaning the same thing. Now this one will only work if we are dealing with gaseous reactants and products. If you're dealing with solids and liquids, this really isn't going to have any effect on it. It's only when we're dealing with the gases. Okay, so again, same type of logic goes on. If I increase the pressure on a system, then it's going to shift in a direction that decreases the total number of moles. Remember, pressure is a measure of the collisions with the container. So if you're increasing the pressure, the way to relieve that pressure is to have fewer particles. The less particles you have, the less pressure you're going to have, the less collisions. So we got to first figure out where or how many particles we have. Well, over here we have one nitrogen, right? The coefficient in front's a 1, and we have 3 hydrogens. So together we have a total of 4 molecules or 4 moles of molecules on the left side. On the right side we have 2 NH3, so we have a total of 2. So I have fewer particles on the left side of my balanced equation. So if I increase the pressure, okay, and that's what the question tells us, if we increase the pressure over here, then it's going to shift to the right because there are fewer particles. Okay, so it shifts to the right. Again, fewer particles means fewer collisions, so it relieves the increase in pressure and actually drops it back down and reestablishes equilibrium. So if we decrease pressure, then it'd be just the opposite. By decreasing the pressure, the molecule is able to spread out a little bit more, so we can have more molecules. All right, so again, let's look at a couple examples of this one. Okay, in the first one we got sulfur dioxide reacting with oxygen, and that's producing sulfur trioxide. And it says, well, what if we increase the pressure? All right, well, again, we got to count the number of particles we have. So we've got 2 SO2s, we've got 1 oxygen. Okay, so total, I've got 3 on the left side. And then over here, I've got 2 SO3, so I have 2 on the right side. So I got 3 and 2. If I increase pressure, it's going to shift towards the side with the fewer, so it's going to shift to the right. All right. Okay, for number 2, it says if the pressure is decreased on the following system, which way will it shift? All right, well, again, we got to first count our molecules. So on the right side here, I've got 1 hydrogen and I've got 1 fluorine. So together, I have 2 molecules, or 2 moles on the left side. On the right side, I have 2 hydrogen fluoride, or hydrofluoric acid. Either way is correct. So I have 2 on the left, 2 on the right. I have equal amounts. When you have equal amounts of moles on both sides, it does not matter whether you increase or decrease. There's going to be no shift because it's not going to matter. If I push it to the right, I still have 2. If I push it to the left, I still have 2. So there is no shift since 2 equals 2. Okay, so this is a unique situation that you occasionally come across, so that's why we put it in here for you. All right, so again, when you have equal number of moles on both sides, an increase or decrease of pressure has no effect on the equilibrium position. It will stay as it is. Okay. Now, one other thing we want to mention here is the addition of a catalyst. Sometimes folks think that by adding a catalyst you are shifting the equilibrium. And we just want to clarify this real quick. If you go back to Module 6, remember that the addition of a catalyst increases the rate of reaction by providing an alternative pathway. If you look down here at the diagram, the blue line represents the reaction without a catalyst. Okay? Starts off with a certain amount of energy. We have to add the activation energy to get it started, and then it will decrease until we have the products. Now, the reverse reaction still follows that blue line, going backwards. If we add a catalyst, we lower the activation energy. So now we're following the red line. So we start with the reactants, they go up the smaller hill here, and then end up as products. Well, the reverse is also true. You start down here at the products, and they go up the smaller hill back to the reactants. Okay, so the addition of the catalyst only increases the rate of the reaction, and it does it for both the forward and the reverse reaction. So as a result, because it does the same exact thing for both the forward and reverse reaction, it has no effect on the equilibrium position. Okay, so don't get tricked by a test question or something if it says what happens if you add a catalyst, because it does not affect the equilibrium position because it's providing that alternative pathway for both the reactants and the products. All right, so now that you've gone through the lesson, you can, of course, attend the tutoring session if you need some more help. You can also use our review sheet in the Resource Center. For this particular assignment, you will be doing a research report, or paper, if you want to call it that. You can find that by looking at the Activity tab in 7.05. There's also a rubric there that will show you how it will be graded. And once you do your research and write your paper, you can then submit it in the assessment or gradebook section in your course. So I hope this was a helpful experience for you, and we look forward to seeing you again soon.